Hello, this is Dr. Christy Patton Lukes, a chemical engineering professor at Missouri S&T, and this series of lessons is for process control. Our textbook for this is the Process Dynamics and Control Fourth Edition by Seaborg, Edgar Mellichamp, and Doyle, and published by Wiley. The, in particular, for this material, I'm going to go through a few examples of dynamic modeling, but really read the textbook. It's got great examples. You definitely want to look at those. We are looking at chapter 2, which is theoretical models of chemical processes. And in the last video, we went through the methodical process for creating. In this example, we're going to be looking at two gravity drained tanks in series, right? This is probably the easiest of the examples that I will be doing, but I want you to try to do this problem before I do it. Okay. So, first, think about what are the things that in this diagram probably are constant. Well, what did you come up with? I think that probably the cross-sectional areas of the two tanks will be constant. I also think that any properties will be constant. Since this is only going to be a material balance, density is going to be the primary property that we are concerned with. Okay, so I have flow coming into tank one, I have flow coming out, I have flow that came out going into tank two and then coming out. Write a material balance for tank one. Okay, so what did you come up with? If density and area of tank one are constant, then the change in mass inside the tank is rho times A1 dH1 dt. And the flow in is W naught. The flow out is W1. Okay, now similarly write the tank 2 material balance. Well, this one should have been easier. So the density remains the same. The cross-sectional area and height now reflect tank 2. In is stream 1 and out is stream 2. So these are great. These are all for known flow rates, WI. Then this would be easy to solve for H1 and H2. Okay. But there are a lot of other cases where maybe I want to add a valve or there's some sort of special, a pump maybe. In those cases, perhaps I have something where I know the flow rate coming out. So perhaps W1 is going to be related to the height in tank one. When there's a lot of hydrostatic pressure, that flow will go fast. When there's very little, it will go slow, and it's probably not linear. And it's likely something such as this to replace this here. And in this case, if we have a variable flow rate due to the hydrostatic pressure, then W1 would still be K square root of H1. And W2 is a similar situation, but it's K for the other flow valve or whatever we've got coming out of there, square root of H2. And so this would replace this in the case where I'm dealing with hydrostatic head driving the flow. Okay. Now, in the first case, if those are just known functions, which would be the case, say maybe if I had a pump or something like that in there, or if the pump or if the height didn't change very much, and so it was relatively constant. those are relatively easy to solve, but in the new case, the one that I've done in red, where I'm dealing with hydrostatic head that is going to be driving that flow rate, now then these are a pair of coupled differential equations, which will be much more challenging for us to solve when we get to that stage. Next, let's do a similar problem, but now then these tanks are heated. I am also going to simplify things, assume that I have constant volume as well as constant properties. That means that if the area is not changing, then those heights will not change. My material balances, therefore, are going to have the time derivatives equal to 0. Take a moment and see what you come up with if you write those expressions. If the derivatives, the accumulation is 0, then we just have in minus out, and so the in and the out have to be equal to each other. Therefore, from tank 1, W0 is equal to W1, and from tank 2, W1 is equal to W2, which must also be equal to W0. Now, what about the energy balances? Again, we are assuming constant volumes and constant properties, and let's further assume that CV and CP are approximately equal. This would be the case of a liquid system. So I want to have the accumulation of energy is the energy flow in minus the energy flow out, plus my rate of heat transfer, Q1 or Q2, through those heating coils. Take a moment, pause the video, and write those balances. These energy balances look very much like the one we did in the previous lesson. So my volume, V1 for the first tank, V2 for the second, rho times C sub P, D T1, the temperature inside the tank, if it's well mixed, should be the same as what comes out, T1, and V2 rho C sub P dt2 dt for the second tank. Now, in each case, those are equal to what came in minus what goes out. So W naught C sub P, T naught minus the reference, minus W1 C sub P T1 minus the reference, plus the heat transfer to that tank. So for the second tank, it's W1 CP T1 minus Tref minus W2 CP T2 minus Tref plus Q2. Now, add in the facts that all of those flow rates are going to be the same if the volumes are constant. And then you can do things like eliminate the T reference, those will subtract out. And we get a simplified expression. The simplified version, the left-hand side remains the same. The right-hand side is now the flow rate, W naught or W1, W2, they're all the same, right? Times C sub P times the difference in temperature, T naught minus T1 for tank 1 and T1 minus T2 for tank 2, and then add in the heat transfer rate, Q1 for tank 1, Q2 for tank 2. So if W naught is well defined, right? If I know W naught, then I can, and I know T naught, then for some disturbance function Q1, or maybe that's my manipulated variable, with that known input, I can then solve this equation for T1. Once I know T1, I can use that answer in here and the second equation. So start here, solve for T1, use that answer in T1 to find T2. So I could solve these sequentially. The key to all of this is knowing how to solve these differential equations. So in our next lessons, we will be looking at just one method for solving differential equations, equations, we will be focusing on the Laplace transform method because it's going to have some extra additional value to the world of process control. So that concludes this video lesson. Thank you very much for your time, and don't forget to read those examples in the book.